Namaste. Welcome to the lecture series on the subject Basic Thermodynamics, Module 3, Part 2, Entropy, lecture number 13. Myself, Dr. Satheesh Kumar, Associate Professor of Mechanical Engineering, Canara Engineering College, Bantwal. So the contents for this topic and the coming two lectures are the numerical on entropy calculations. So let us solve this problem. 1 kg of water at 273 Kelvin is brought into contact with a heat reservoir at 373 Kelvin. When the water has reached 373 Kelvin, find the entropy change of water, the heat reservoir and the universe. Okay, it's a very simple problem. So 1 kg of water is brought into contact with the heat reservoir at 373 Kelvin. Now here you have to understand one thing. So water is considered as a system, whereas it is coming in contact with a heat reservoir. So for a heat reservoir, as all of you know, if you add or remove some finite amount of heat from that, so its temperature is not going to change. That means when 1 kg of water is brought in contact with the reservoir, temperature of water will increase, whereas the temperature of the reservoir will not decrease. So though it gives out some heat, so it is at the same temperature 373 Kelvin, but water is absorbing heat and its temperature increases from 273 to 373. So here heat given out by the reservoir is equal to the heat absorbed by the water. So you have to understand, you see how does the temperature of the water increase? Because it absorbs heat from the reservoir. So a reservoir loses some heat, same amount, both are same. Amount of heat absorbed by water is equal to amount of heat lost by the reservoir, but reservoir temperature doesn't change. So this process takes place at constant temperature for the reservoir, whereas the water temperature changes. So try to understand this basic. Okay, now let us calculate the entropy change of water when the water also becomes equal to 373, because it is coming in contact with the reservoir. So its temperature also becomes equal to that of the reservoir temperature. Then the entropy change of the reservoir and of the universe. Universe means you have to calculate the sum of entropy change of water plus heat reservoir. Okay, this is a solution. T1 is taken as the temperature of water, T2 is the temperature of the heat reservoir. Heat transfer occurs from the reservoir to water, and it takes place through a finite temperature difference, irreversible, because you cannot supply heat back from the water to the reservoir. The entropy of water would increase because it gains heat, and that of the reservoir decrease because it loses heat. Okay, and the entropy change, net entropy change of the water and the reservoir together will be positive, definite, because of it is a irreversible process. Okay. Now let us calculate the entropy of water. So this is a diagram. Heat reservoir at 373 Kelvin, water taken at 273 Kelvin. Q is the amount of heat transferred from the reservoir to water. Now entropy of water, so since water, its temperature changes from T1 to T2, so you have to use this formula, integration from T1 to T2 mCp dt by T. So this is a standard formula for entropy calculation when the temperature changes. Okay, so m is okay, before that let us integrate this. So integration of 1 by t with respect to dt is ln t, and applying upper limit and lower limit you will get ln t2 by t1. I hope all of you know how to integrate this. So substituting m is 1 kg, Cp of water is 4.187, and substituting for T2 and T1, you will get the entropy change of water as 1.3068 kilojoules per Kelvin. Clearly you can see the entropy change is positive, because whenever the entropy change, temperature increases for the substance, the entropy change is positive. Okay. Now the temperature of the reserve, okay, that is what I told, reservoir remains same irrespective of the amount of heat removed from the reservoir. So we will calculate the amount of heat absorbed by the system from the reservoir. Means what is the heat absorbed by the water here. System means what? Water. So the system word here indicating it is water. So that is nothing but Q is equal to mCp into T2 minus T1, because water initially at temperature T1 increases to its temperature T2. So this is the temperature difference, right? And Cp is the amount of heat required to raise the temperature of unit mass of the substance by 1 degree. So this is for 1 degree. So you have to multiply by delta T, which is nothing but T2 minus T1. And Cp is for 1 kg. So you have to multiply it by mass also. See, Cp gives clear idea. mCp delta T. Cp is specific heat. Heat required to raise the temperature of unit mass of the substance by 1 degree. Unit mass. If mass is m, mCp. It is mCp is the total heat required to raise the temperature by 1 degree. If the temperature is delta T, so mCp delta T. So delta T is nothing but T2 minus T1 here. So if you substitute, so this is the amount of heat absorbed by water for 18.7 kilojoules. Now this is positive for water but negative for reservoir. Why? Because reservoir is giving the same amount of heat to the water. So the entropy change of the reservoir, so it becomes minus Q by T2. Now here you see there is no mention of T1 and T2. Only T2 is there, because temperature for the reservoir doesn't change. It remains at 373, though it gives out some heat. This is very, very important. Try to understand this. This is for the reservoir. Okay, or for anything of which the temperature remains constant during the heat rejection or absorption. Try to remember this. So you get the answer as minus, since you see entropy is decreasing, heat is rejected, so entropy change has to be negative. So minus 1.1225 kilojoules per Kelvin. Negative sign indicates that entropy decreases. Now entropy change of the universe is nothing but delta S water plus delta S reservoir. Okay, if you substitute, you will get it around 0.1843 kilojoules per Kelvin. Okay, that is 1.3068 minus 1.1225, so it is 0.184. This quantity is positive. Okay, so that way initially itself I told you that the answer will be positive. Now let us solve this problem. 2 kg of air is heated from 27 degrees Celsius to 427 degrees Celsius, while the pressure changes from 100 kilopascal to 600 pascal. Calculate the change of entropy. So R, constant R, is given as 0.257 kilojoules per kg per Kelvin, and Cp for the air is given as 1.005 kilojoules per kg per Kelvin. Okay, so 2 kg of air is heated from 27 to 427 degrees Celsius. So there is a direct formula to calculate the entropy. Okay, so this is the given data. So 2 kg, so always better you put it or draw a table and mark it, write it in the inside the table. So m is equal to 2 kg, T1 is equal to 27 plus 273, 300 Kelvin, T2 is 427 plus 273 is equal to 700 Kelvin, and pressure is given as 100 and 600. Okay, P1 and P2. So the general equation used for the calculation of change of entropy when there is a change in pressure and temperature is S2 minus S1 is equal to mCp ln T2 by T1 minus mR ln P2 by P1. So this you have to remember. Okay, if you make proper substitutions, so you will get the answer as 0.7821 kilojoules per Kelvin. So that is why here the two temperatures are given and two pressures are given, and R is given as well as Cp is given along with the mass. If these quantities are given, so directly you can use this formula to calculate the change of entropy. Now let us solve this problem. 10 grams of water at 20 degrees Celsius is converted into ice at minus 10 degrees Celsius. So water is at 20 degrees Celsius, try to understand this, is converted into ice at minus 10, very important, at atmospheric pressure. So all of you know that ice formation takes place at 0 degrees Celsius at atmospheric pressure. So that is what you have to understand and analyze the problem. Water at 20 but ice at -10, and the conversion taking place at atmospheric pressure. That means water to be brought from 20 to 0 first, at 0 water to 0 ice, and then 0 ice to -10 ice. You see, very interesting. Assuming specific heat of liquid water to remain constant at 4.184 joules per gram or kilojoules per kg, both are same, and that of ice to be half of this value, and taking latent heat of fusion of ice at 0 degree Celsius to be 335 joules per gram or kilojoules per kg, calculate the total entropy change of the system. Okay, very interesting. So these are the given data, so better always note down in the table form. Mass 10 gram, water is initially available at 20 degrees Celsius, that is 293 Kelvin, ice to be formed at -10, okay, that is 263 Kelvin, Cp water is given, so I told you it's same value for the in kilojoules per kg also, similarly Cp of ice, okay. Okay, now the problem is better explained by the help of a TS diagram. So you can see here, so this is the temperature axis and this is the entropy axis. So your entropy change takes place in 3 steps. See, whenever there is a phase change involved, okay, so entropy change may take place in 3 steps. So how I will tell you. So initially water is at 20 degrees Celsius, all of you know. So this is the water point. State 1, water at 20 means 293 Kelvin. Now the process of conversion of water to ice is taking place at atmospheric pressure, and you know that atmospheric pressure, the conversion takes place at 0 degree Celsius, which is nothing but 273 Kelvin. So water is at 20, but you have to bring it down to 0. So this is what happens when the water temperature is brought down from 20 to 0. This is the line, okay, because here heat is removed, so entropy decreases. You can see entropy is decreasing from here to here. So this is the entropy change of water from 20 to 0 degree Celsius. Try to understand that water from 20 to water at 0, water, okay, make it clearly. Now here when the phase change takes place, there is no change in temperature and pressure, that I told you earlier, right. You will come to know in depth about this under the pure substance chapter. So 2 to 3 is the ice formation. So during the phase change or the ice formation, latent heat of fusion will come into picture. So the amount of heat to be removed from water, because initially it's the water at 0, so it forms ice at 0. So till then you have to remove heat, so that is called as latent heat. So here what to come into picture is Cp of water. So the water 20 to water 0, Cpw will come into picture. Here latent heat will be removed, right. So every 1 kg, so the latent heat of ice will be removed. Then when ice becomes water becomes ice at 0, so this is water at 0 at 2, ice at 0 at 0.3. Now you are removing the heat from the ice, so that its temperature reduces to -10 at 4. So -10 means 263 Kelvin. So here Cp of ice comes into picture, because Cp is nothing but specific heat. So this is the amount of heat to be supplied or removed to change the temperature of the unit mass of the substance by 1 degree. You see, if you want to increase the temperature, you have to supply the same heat by quantity called specific heat. If you want to decrease the temperature also, you have to remove the same quantity of heat called as specific heat. So I hope it is very clear to all of you, okay. So entropy change of water we will calculate first, that is delta S1, as it is converted into ice. Okay, it is all together, okay. So entropy change of water, that is system, as taken the system, when it is converted into ice, so it will be having 3 steps, okay. Delta S total is equal to delta S1, so that is what I wrote here. So this is the entropy change during the formation of ice, from 0 water to 0 ice. This is from 0 ice to -10 ice. You see, very clear water 22, let me take a different color. This is water 22, water 0, water 0 to ice 0, ice 0 to ice minus 10. I hope it's very clear for you. 3 steps of entropy change you have to calculate. First step, temperature change is there. Second step, delta S2, water 0, ice 0. Is there any temperature change? No. Be careful about this. Then delta S3, ice at 0 to ice to minus 10, temperature change is there. Note it. Okay. So together delta S of the system will be delta, this is for water to ice, delta S1 plus delta S2 plus delta S3. Okay. Now delta S1 is the entropy change of the system as it is cooled from 20 to 0, which I explained already. So delta S1, so you have to write as integration from 293 to 273. Initial temperature is 20 degrees Celsius, which is T1, and this is T2 is 273, 0 degrees Celsius. MCP dt by T, like in the previous problem. So ln T2 by ln T2 by T1. So I don't explain much about this. Substitute, you will get it as minus. You should get it as minus because the temperature, final temperature is less than the initial temperature. This quantity ratio is less than 1, means ln of a quantity less than 1 is always negative. So the answer is always negative. So it is minus 2.958 into 10 to the power minus 3 kilojoules per Kelvin. Now delta S2 is the entropy change of water when it is at 0 degrees Celsius to become ice at 0 degrees Celsius. No temperature change. So it is just MQL by T. So MQL is nothing but total amount of heat removed during this conversion process. So M is mass of ice, which is 10 kg. Okay. So here also you have taken M 10 kg here in the previous calculation also, right? Oh sorry, it is 10 grams. 10 grams, sorry, not 10 kg. So 10 grams is converted into kg by dividing 1000. So here also M is 10. Okay. And QL is nothing but the latent heat of ice. So this quantity is nothing but latent heat of fusion of ice 335, and this whole thing is a heat to be removed, and it is taking place at constant temperature of 0 degrees Celsius or 273 Kelvin. Okay, so MQL is the total heat removed, total for 10 grams. Every kg it is 335. So you have to multiply by 10 by 1000. Okay, so I hope it is a very basic calculation, and since heat is removed, so you have to put a minus sign here, and the entropy, that is very important. Minus sign is not there in the formula, but here first case delta S1, you need not put minus sign. Automatically you will get the minus answer here. Can you see here? Minus you will get automatically because of the integration, but here you won't get. So but you should know, you should remember to put minus sign, so that you will get minus 0.0123 kilojoules per Kelvin. And delta S3, that is entropy change of entropy change of ice at 10 to ice at minus 10. Sorry, ice at 0 to ice at minus 10. Okay, ice at 0 to ice at minus 10. So it is delta S3 MCP ice you have to take. So here you have taken MCP water 4.184 in calculation number 1 or A. So here MCP ice, again here you can see initially ice at 0, then ice at minus 10. Temperature is decreasing, so you have to substitute, and I am sure that you will get negative answer, because here again the entropy is decreasing because temperature is decreasing. Entropy is negative because temperature is decreasing. Okay. Okay, now let us calculate the total entropy change of water as it is converted into ice. Means from water at 20 to ice at minus 10, means you have to add all the 3 steps of entropy change. Water to water, water to ice, ice to ice. Delta S1, delta S2, delta S3, since all are negative quantities here, so you will get a negative answer itself, minus 0.01604 kilojoules per Kelvin. So maybe I have taken a bit more of your time, more time for explanation, but I hope it is very clear for you. You will understand how to solve this kind of problems. So with this I conclude this lecture number 13, and we will continue with the more numericals in lecture number 14 and 15. Thank you.